Good afternoon. Oh, come on. Good afternoon. Thank you. And thank you all for coming today and spending your afternoon. Really appreciate it. I'm Adam Glick. I'm a senior program manager focusing on resiliency in Azure, and we're going to spend today, or at least the next 75 minutes of today, talking about designing your applications in Azure for high availability and scalability, making sure that you can have your apps be online and keep your uptime as high as possible within it. I put my contact information on the slide. That's not required. I do that because I want to hear from you. So there's a slide at the end where I'll talk about filling out your evaluations that I hope you do. But also if you have any questions to follow up afterwards or something comes up, you can reach out to me, whether it's on GitHub, LinkedIn, my email at Microsoft, or on Twitter. I will tell you that Twitter's probably the one that I check least. But use whichever one you like to get a hold of me, because I certainly want to hear what you like to hear more of, what you'd like to see us doing, so that we can make better content for all of you. That's what I do. With that, let's get started. Three major things we're going to go over: designing your applications for high availability using the Azure platform, understanding best practices, what you should be doing, and also understanding what are some of the things that you might not be aware of that are pitfalls, and how do you avoid those to make sure that you can do things the right way and not get bitten by some of the gotchas that sometimes people run into the first time they design something in the cloud versus on premises that they may be more aware of. And then talk a little bit about some of the inner workings of Azure, what's actually happening with some of the services and how we've designed some of these things for high availability. One note is that I spend most of the time in the session talking about IaaS, infrastructure as a service, and building that out as opposed to PaaS services. PaaS services, for the most part, take care of the high availability themselves. There are some things you can do there, but if you have questions about that, ask me afterwards. But I'm really going to spend most of my time talking about doing infrastructure as a service and how you do that with high availability in Azure. And with that, let's get going. High availability. What does it mean to you? Everyone actually has a different definition of this. I mean, if you think about uptime, ask yourself, what's the availability of the application that you want to do? And that's a business requirement. I won't drill in too much into how you define that, because it's going to be different for every person in this room. But basically remember that you're going to define what that is, and that's going to define how complex a system you want to build, how many nines you want to be designed for, what level of fault that you want to be able to handle with your system. And so think about what those different things are, because it's going to alter what architecture you're going to use. And we'll talk about a number of different architectures today and how you'll use those different architectures to solve for different levels of faults that you might have happen within an organization. This is part of the resiliency continuum, so some of this is kind of foundational. I just want to make sure we're all on the same page about stuff. So resiliency continuum is basically everything that has to do with keeping your applications online. This talks all about high availability. I'm not going to talk about backup or disaster recovery. There's some links at the end of this deck that will talk about sessions that cover that content. Another talks here at Ignite that you can check out that will cover those. But the thing that I want you to take away is basically RPO and RTO. That's recovery point objective, recovery time objective. For high availability, the target is 0. So the goal is basically you are always online, and any fault that happens does not take your system offline. And that's what we're going to talk about designing systems for today. If you're in a situation where those have gone offline, you're in a disaster recovery scenario, and you can check out the talk that was done yesterday that talks about those pieces on it. So think about how do you make sure that as things happen, as servers go down, as disks fail, as you get high levels of traffic, that you can make sure that your services continue to serve up the applications that you've built. So when you think about the cloud and you think about doing that, you need to start thinking about something that, for anyone who's worked in manufacturing, anyone work for a manufacturing company? Quick check. A few folks in the crowd. You're probably very familiar with MTBF, mean time between failure. But that's what you need to start thinking about, because you're going to have a lot of different servers. And as those servers run, you're going to think about how long does it take between when these things fail. And the reason you want to think about that is the higher that number is, the bigger the amount of time between when things fail, that's how less likely that failure is to occur, and you need to think about that when you're designing for your availability. The more rare that occurrence is, the more you have to decide, is it worth the cost of designing a system that's going to protect you from that? The more common that failure is, the more you're going to want to be able to build a system that's able to handle that. Something like a disk failure, or say dropped packet in a network, might be fairly common. So you want to make sure you design for that. Something like a data center burning to the ground, hopefully is a very uncommon thing that happens for you. And so you have to decide, do you want to be able to design something that spreads across regions, multiple data centers? We'll talk about all those different designs and how you do it, but you'll make those decisions because they'll impact the cost and the design of your architecture, how complex it is, how many different things you need to manage and set up automation for. This is true for on-premise and on the cloud. Obviously, we'll be talking about the cloud here, but a lot of the principles and the design techniques we talk about will be the same, although the technology that I'll be showing you is how Azure does those things and makes it easy for you. And just remember, failure of hardware is inevitable. When we say MTBF, that's mean time between failure, because everything fails at some point. Never assume that nothing will ever, something will always be available. Something will fail always. It's just a question of when, so plan for it. So some good design principles when you design for the cloud. And you think about okay, what are the things you should think about architecturally? You think about doing it. And we'll step through a bunch of these, and then we'll drill in deeper into actually talking about how you actually make them happen. But if you take nothing else away from this talk, no single point of failure. So I run into this one all the time when I'm talking to people, and everyone conceptually gets that, right? If you've got one machine, we've been doing this for years on premises, you always have two machines, and you link them together to make sure you have no single point of failure. Remember that it's not just the virtual machines you need to think of, it's everything in the infrastructure that you're building. We'll talk later on about how to make sure you don't have single points of failure in storage. When you think about what you're doing in networking and load balancing, until you have no single points of failure. It's no single points of failure throughout your entire stack. And again, when you talk about that blast radius of how big a event you want to protect yourself from, you also need to think about what does that mean in terms of, is a region a single point of failure for you? Do you want to be able to survive something like a region service disruption? Because that's one single point. And if you want to do that, there's some design characteristics that we'll talk about how you build those systems. But again, different systems, different size of scale that you want to be able to design for. The next one is your state should stay at the edges of your app stack. When I say app stack, it's important to think that it's not just the edge. You don't want that always on the client, but you think about basically the ends, so basically your presentation layer, your client, or the database layer. Don't put it in the middle. You want stateless services. So make things as stateless as possible. Best place usually is to store your state in a database. If you're something that does a lot of transactions moving fairly quickly, you may decide to put your state in something like a NoSQL database versus storing, say, your transaction data or your financial data and put those in something like an RDBMS, a SQL database. That you don't have to pick one database. You pick the right thing, but make sure you store those in one particular location. Don't store them, if you do, don't store them throughout the app. If you create stateful applications, you're creating things that are brittle. You're creating things that when those pieces of the application fail, your customers will be impacted. So keep your state away from the center of it. It will allow you to be more scalable. It'll make it faster, and we'll talk about that. Talk loosely coupling your components. If at all possible, make sure they're loosely coupled. What do I mean by that? Is if you're going and you're passing state along through, so you've got a monolithic 3-tier app. Everyone's built one at some point, 3-tier app? Yes, hopefully. We'll talk a lot about those. When you have a 3-tier monolithic app and you're storing state, like you store state on the server, then if that goes down, you're impacted. It also means that if something else in that stack goes down, if things are reliant upon that, you've impacted everything in that chain. If you make things loosely coupled, then losing one part doesn't fall away from somewhere else. So this is a little bit more of like a service-oriented architecture or microservices. We'll talk about both today, but if you think about it, if you take microservices and basically instead of passing things between load balancers, which is typically what you'll do between tiers to make sure you have scalability, you're going to use things like queues. Because if you put it in a queue and that next tier isn't available for some reason, it'll just stay in the queue. When that next tier becomes available, it can pick it up. You're resilient to that failure that happened, versus if it goes to a load balancer and there's nothing below that load balancer, if that tier has failed for some reason, then your service is offline. And it didn't matter that your other tiers were available because you've lost it. Your customer packet just goes to nowhere and dies. So think about using queues instead of load balancers. It does require a different bit of architecture, and you have to choose what's right for you. But that will help you build things that are loosely coupled versus strongly coupled. Process your content centrally and then deliver it locally. So if you're think about your data. If you distribute your database everywhere, you're going to have all these little bits that you have to piece together. It's super easy with the cloud to put it in one place, process that, and then send the data places where you want to deliver it. So if you have all your data in one central place, you're going to avoid some of the challenges that you have with databases of spreading them out. We'll talk later about how if you need to spread them out for any number of reasons, including disaster recovery, how you do that. But that's going to make it more complex. Again, everything's on a continuum of the complexity of the cost you're doing versus your ability to move quickly and easily. So you process it centrally, but deliver it locally. And whether that be making sure that you're processing that data and then, say, putting it out to a storage file that you pull it out of, or you have a secondary database that you actually put that data available in locations that are closer to your customers, or whether it be using something like a CDN and actually having the CDN cache that content that's closer to your customers. They'll get a better experience out of it. You'll get more scalability out of it. And we'll talk a little more about that later in the presentation. finally, just a good kind of, or not finally, but next one is a good rule of thumb about automating. Make sure you automate everything. I know, especially when you're doing development, super easy to go in there, make a quick configuration change, or just develop and push it. It's a bad habit. It's fast, it's easy, it's not repeatable. If you take a look at failures that happen with systems, if you take a look at even data center level failures, if you take a look at industry-wide statistics, data center-wide failures, over 50% of them are human error. People make mistakes. We should manage code, code should manage machines. Get in that habit, you'll be able to be more scalable, you'll be more available, you'll be able to bring your systems up faster, do that, and we'll talk a little bit about how you can do that in Azure and using ARM templates to do it. Me personally, I'm a fairly trusting guy, but stick with trust and verify. Everything you do, make sure it's actually happening. We'll talk about how you monitor your services a little bit. We'll talk about what you're doing with load balancing, make sure things are up, that you have to make sure that not only you've built the system that you intended to build, but that you're verifying that that is happening and that it's staying that way. And there's a number of different services that you'll verify different ways, and we'll talk through each of those about how you do that and make sure that you're doing it. But you have to verify not only that your system is there, but it's delivering what you want it to do. And the last one is really one of these big changes that's happened as you move to the cloud versus you built things on premises. And that is, think about scaling out versus scaling up. So I'll drill into that a little bit. When you think about traditionally on premises, how many come from an on-premises background? No, almost everybody? Cool. So traditionally, we've scaled things up. So easy example of this is the database server. You got the database, and you bought the biggest database server you could. And you bought the biggest database server you could because you can't scale the database server. Technically, you can go and you can shard it, but that's a whole lot of work that you probably don't want to do unless you hit the point where you have to. So you bought a really big box, and it was probably highly underutilized, and you made sure that you put the best drives you could, that you got the best network cards, you put redundant power supplies in it, you did everything because you needed to take care of that server. And that was scaling up. And if you hit the point where all of a sudden you reached the limits of that server, you probably went out and you bought an even bigger server. That's scaling up. You can do that in the cloud if you want. We make it easy in Azure if you want to go within an instance family and just scale up and move something to a larger instance size. But the problem with that is, one, your cost, because that cost that you do isn't a linear scale. If you spin up a second server is the same, you just double your cost of one. But if you scale it up to a server that's twice the size, a twice the size server is not twice the cost. It's much more than that. So you need to think about what's the cost impact of what you're doing. When you scale horizontally, you don't have that impact. The other side of it is, frankly, that it's brittle. When you scale up, yes, you may be able to handle load. So you've handled the scalability issue that you want. But you still haven't handled the high availability piece of it. You still have one server. And when that one server has something happen to it, remember, hardware will fail. Bad things will happen. And when that goes down, you don't have another one there. Or if you do, that's extremely costly. If you have it spread out, if you have multiple servers, you'll avoid that. And we make that easy with things. The VMSS stands for VM scale sets. We'll talk about that a little bit later, but that's basically an easy way for you to define what a tier of your application is and how you stamp out and how you grow those things horizontally and how you auto-scale those. But the best description I've heard of this is the description of pets versus cattle. So when you think about things that scale vertically, those servers that you think of them like a pet. You probably know the name of them. I'm willing to bet if you ran any on-premises infrastructure, you actually knew the name of the server that you would go and you would connect to. You knew it. You took care of that server. If there were problems with that server, you would log into the server and you would check, hey, what's causing my high CPU? What's causing RAM usage or my disk to be highly utilized? And you'd be going in there and you'd be fixing that server because that server is something that you needed to take care of. And that's the vertical scaling view that you take on things. That's very different than a scale-out version. The scale-out version is like cattle. So cattle you don't give names to. Cattle are basically a commodity. If you need more cattle, you buy more cattle. You need less cattle, you make some hamburgers. It becomes it's super easy for you to go back and forth, and the cloud enables that. What it basically is, it removes that capacity concern and that I need to have this machine and I need to keep it running. The easy example for this is when you think about patching. So in the world of pets, in the world of on-premises servers, you've got a new patch. You've got your patch that comes out each month, whether you're running on Linux. That's just as true for Linux as it is for Windows. You've got your patches, and you're going to go patch that server. What do? You're running some sort of management suite that you're patching that server. You're logging in. You're doing it manually. But you're patching that server all the time. You're taking care of it. It's a pet. In the world of cloud, you don't need to do that. You've got a new server. There's a new version coming out. You've already got these things templatized. You just spin up a new server that's the whatever it is that you want, it's already patched. It's already got the latest version. If you go into Azure and you select, say, Windows Server 2016, you launch it, and it is the latest patched version. And then you install whatever PC you want, you connect it into your infrastructure, you take your old one, and you just throw it away. You kill it. They're cattle. They're commodities. And so it allows you to think about how do you manage and scale your infrastructure. That's the way you scale out your infrastructure, and that's the way you can manage your infrastructure. And that's why horizontal scaling makes it really easy and a much better way to manage things at scale as you work within the cloud. So that said, that means that there's certain workloads that work really well in the cloud, and there's certain ones that you want to think a little bit more about before you do. So things that work really well in Azure, things that work well in the cloud, are things that you've built. Because when you go and you build a new application, you can follow the principles that we're going to talk about in this talk, and you can build it so that it's built for the cloud, that you're using the right principles to make sure that it's scalable, that you're taking advantage of what the cloud provides to you. If you're using something that's software that someone else built, it can be designed for the cloud. If you are, then you're fine. But a lot of legacy applications, how many people run an application in an organization that is at least, say, 6 years old? So those are going to be a little bit more challenging because they probably weren't designed for a cloud. They probably were designed for horizontal scaling within an organization. Now, you can lift and shift those to the cloud, but what you're going to do to maintain high availability with those is going to be different. You're going to have to think strongly about the database layer when we talk about databases and how you make sure that the data availability is there. But there may not be a lot that you can do for, say, the front end or the logic tiers. If they've designed those to be stateful applications, they are somewhat brittle, and there's not a lot that you can do about it because you don't own the code for that. So you're going to have to think about that as you design and as you think about what's the availability targets that you're doing with those older applications if you lift and shift them to the cloud. So the last one is designing around a single state data store. That's what we talked about before, about making sure that you're storing state and you're keeping that in a data layer, that you can keep your applications as stateless as possible because that's going to give you the most flexibility and ability to scale and handle faults as they happen. So today's talk, we're going to go through 3 basic areas: compute, networking, storage. These are 3 kind of core areas for your infrastructure, and these are 3 different areas where you can have faults that come in, you can have failures that happen, and how you're going to design and protect around each of them. You could have a fault happen in any one of them, or due to my awesome PowerPoint animation skills, you can have faults in all of them. So let's talk through what you can do. Let's start with compute. So first thing, when you're thinking about your compute, I'll ask a dangerous question here. How many of you have all of your VMs running in an availability set? Okay. If I can get everyone in this room to move your VMs into an availability set, you will do yourself a great service. So we'll talk a little bit about what that does for you, but the important thing that you need to know is you need to create the availability set. It needs to exist when you create your machine. If you have an existing machine right now and it's not an availability set, you can't move it into one. You'll have to recreate the machine in the availability set. Every time you create a machine, you should create it in an availability set, even if you're only creating one machine. This will allow you to plan for the future, to plan for future scalability, and to protect yourself for availability. Because if you want the Azure SLA, which is 395 on VMs, you need to have at least 2 machines in an availability set. So it's important that you have those there. Even if you're going to run one machine, you decide that you're not going to put yourself up for the SLA, that's okay. But then realize that your ability to scale up in the future means that you need to have that availability set already created. It's already there when you go in and you create a VM. It's there in the portal. You can just choose availability set, create a new one, or if you're doing it command prompt or in an ARM template, you can just create it there. But you have to make sure that you do it. Put everything in an availability set. Just make that your new normal. And the thing to remember is don't put them all in the same availability set. So it's tied to a role in your application. So for instance, all of your web servers is part of an application. Basically everything that could be a carbon copy of the other ones, you want an availability set. So all of your web servers would go in one availability set for the application. All of your business logic, they would go in an availability set. So you'll do separate availability sets. You won't put them in the same one because an availability set, you want to make sure that's how it scales things out. That's how we know that we're protecting your application from the various layers of faults that can happen. So the big thing that it does is it spreads you out across fault domains and upgrade domains. So these are 2 things that you need to be aware of in Azure, because these will help increase your availability. So here's a chart. I put these both up here because some of you may be running in the classic portal, that's ASM, and some of you may be running in ARM, that's the current portal, portal.azure.com. So if you go in there, the numbers are slightly different between the 2, and that's why I put both of them up there. but the thing to understand is the difference between fault domains and upgrade domains. So you can think of a fault domain as a dedicated set of hardware. You can think of it as a rack or a cluster of racks, but it's a set of hardware. And when you spread yourself across fault domains, that means that you've eliminated the ability for a failure at that level to actually impact your application. If the rack went down or if the cluster went down, if you're spread across fault domains, that means that one VM might be impacted. But if you've got an availability set and that availability set spread you across multiple fault domains, your other machines will be okay. If you didn't use an availability set, you could all end up in the same fault domain, which means if a cluster went down for some reason or a rack went down, you could lose all of your VMs. So this is a way of making sure that an unplanned failure at the cluster level will not impact all of your machines, that you can separate them out. That's what fault domains will do for you. Update domains are about planned updates. We do patching every month, sometimes more frequently if there's a hot fix. So we're doing updates. Now, just like you update your machines run on our hosts. Our hosts need to be updated as well. We need to protect the infrastructure that all of you run your applications in. And so when we go and we do those updates, that can impact the machine. Now, we've done some really cool stuff recently in order to make those updates as fast as possible. Sometimes as little as 30 seconds. It can actually happen faster than the timeout on a TCP packet. But realize that those updates will happen. There'll be updates that happen underneath it. And so to make sure that your applications aren't impacted, if you're in an availability set and if you spread yourself across update domains, and simply a slider in the portal, you can just choose how many update domains you want to have available. That will mean that we do each of those one at a time. So you can choose what percentage of your application might be impacted. You can limit the scope of what could happen to you. So in ARM, which is what I build most of my stuff in, and I'd recommend if you can to start building all of your applications in ARM, you get a choice of up to 20 update domains. So you can choose that a very small percentage of your infrastructure would be impacted by that, and that'd be about 5%. Fault domains, you have 3. So if there was an unplanned failure, I'll take questions at the end. That's okay? If you had an unplanned failure that would happen, it could at most impact 1/3 if whatever's in that fault domain. So it's important to spread across both of these, and when you set up an availability set, it'll let you choose these numbers. So you can set that up and have that configured, and then when you start up your new VMs, they'll just automatically be positioned in these. If you set up an availability set, your next VM, when you start it up, will automatically spread to the next one. You don't have to choose which update domain, which fault domain they're each in. We'll do that for you. But you have to make sure you've set up an availability set in order for us to do that for you. Another reason why making sure to set up an availability set is key to making sure you get the most 9s out of your availability with your applications in Azure. Let's talk a little bit about deployment scale. So 1 VM. Every application starts here. I know all the ones that I've ever built do. You have one machine, you go, you built it, hey, it works. That's like development work. And that's great. That's not highly available. You're back to that brittle state. You got one single point of failure. If you take nothing else away, single point of failure, always bad. So you put in a second machine. Okay, we got 2 machines. What do you do about that? Are they in the same fault domain? Same update domain? No, like from the last slide, you probably guessed, put that in availability set. Set them up. Regardless of how many you're going to have there, have that configured so you can. But once you have that, it's important to realize those machines, how does your traffic know how to get there? And that's putting a load balancer in front of it. So that's that 3-arrow design that I have above there. You're going to think about always using a load balancer because if you've got an availability set, load balancers have a thing called backend pools. And backend pools, you can point to an availability set and basically say, hey, the traffic that comes here can go to any of these in the backend pool. And I'll show you some more about that later, but realize that that's the way that you handle that is you have multiple machines, making sure your traffic goes to the right place. So that's pretty quick and simple. As you start to scale up from there, so we'll zoom out a little bit. So now you're taking a look at your whole application. So the person there is your user. The arrows there you're seeing kind of pointing at each other, that's traffic manager. That's DNS. So by using DNS, Azure DNS is programmatically accessible. So you can go and you can configure that and edit it as you want when you want. So users will hit your DNS. DNS will point it at a load balancer. You always want to have a load balancer. Even if you have one machine, which of course will be an availability set, you want to use a load balancer. And the reason for that is very simply, what happens when you want your second machine? If you use the IP address that's tied to your particular VM, then when you start up the second VM, how are you going to handle the load balancer? You want to put a load balancer in front of it, even if there's one machine, because you're designing for scale. You're designing for how do I make sure in the future I'm always protected. So they got the load balancer. In this case, we set up a virtual network. Anytime you're designing a system, start with the network. You don't want to get to the network later. You're going to define what the network is. You're going to define the CIDR rules on that, how big your subnets are going to be. Don't think about what the subnet you need today is. Think about the subnet you need as you scale out the application. Because once you've set the subnet and you've set the addressing space for that, redoing that, changing that is a lot of work. Save yourself the trouble. Set it up when you start. If you use the default, because you'll always be put, if you're doing it in ARM, you'll always be put in a virtual network. If you're using the default, remember everything that you start is going to be put into that default network. You probably don't want all your applications put in the same network. You want to be able to manage what those are and how those networks talk to each other. So start with the network layer and plan it through. Be planful about what you do with your subnets and make sure that you've defined them for each tier of your application. Even if you're not using them today, you can add subnets to things. You can add subnets later, but you can't moving things between the virtual networks. That's a much more painful process. So avoid that. In this case, we put everything in one subnet. That's great. So how do we scale it up from there? What's the next layer as we start to grow and scale our application? Well, now we're breaking out a little. So we got the front end like we had before, but now you'll notice there's a second load balancer. We're using an internal load balancer. So now we've got separation between two tiers. We've got a data tier, SQL servers, and those are sitting in a different subnet. So I can protect those. This isn't a network security talk, but if you talk to some of the security folks or come find me afterwards, I can talk to you about the importance of separating those pieces and not putting everything in the same tier. And you have a load balancer between the two, so you can balance your traffic as it goes between them. We've also added an Active Directory, so you can think about what you're doing in terms of authentication and management of users within this environment. And so we're starting to scale up. This probably looks a lot like some of the things that you may be used to today. You also notice there's no one single server for anything. No single points of failure. Even with Active Directory, we've got two of them in a cluster together. And then finally, let's think about how we scale it from there, because our single point of failure and all that, which is kind of hidden detail, was the region that you were in. That was all in one region. So what happens if we want to look at moving this to a second region? And not moving it as much as expanding it. And so here, you'll notice, here again, why the DNS is important. The DNS at the top is then spreading you to load balancers, and you're pointing it to two separate regions. And in this case, the one we're looking at is kind of an active-passive design. What's the dead giveaway for an active-passive versus an active-active design? And we'll talk about these more later. One, we're doing asynchronous replication, which means that the two SQL databases are not up at the same time, or they're up at the same time, but the data is not synchronized. And you'll also notice that in the second region, we have many less machines. It's not that it's the same design in both places. You have what's kind of like a pilot light. You have another region that's set up, and if you need to, you can scale it up when you need it, but you're not running a bunch of infrastructure for no reason in that second one. That's an active-passive design. We'll talk about both active-passive and active-active a little bit later, but that's the dead giveaway in this one. So I talked about VM scale sets, and I want to drill in a little bit more on that. This is your way to do auto-scaling in Azure. So we talked about the cattle. You have the same set of VMs, so it's by tier. The same way that you did your availability set, same kind of rules apply. So you're saying, hey, this is my web tier, this is my logic tier, whatever it is. It's the machines that are all the same, and you'll define that. You'll define the operating system for it, both Windows or Linux, that you're going to be using for that. And you'll define the rules around how you want that scaling to happen. You can do this through an ARM template. You can also do it through the portal now. There's portal experience. And you can set things like, what's the maximum number of machines I want to set up? This is really useful for protecting yourself from things like, because the way it scales is you can set it for some sort of metric. So let's use CPU utilization as a good metric. And you say, hey, if I'm at 75% CPU utilization or more, I probably want to scale up. So start up another machine. So go spin another one up. And you can say the inverse as well. If my machines are running at less than 10% CPU utilization, these are configurable, of course, then I want to scale down, take one out of the set. So you can scale, but it also gives you a maximum limit. So let's say you had a bug that pegged your CPU. So it spins up another machine, hits the bug, pegs the CPU, another machine. You don't want to wake up in the morning and find out there's 1,000 machines that got spun up simply because it just kept scaling and scaling and scaling. So we give the ability for you to put a cap on it. And you can set up monitoring as well, and so you can be alerted if something's happening. But we give you the ability to kind of protect yourself from something like that might happen. But set these up, because if you set up the VM scale set, again, that means you're scaling automatic, rather than you having to go in and say, hey, I'm noticing I'm getting a lot of CPU utilization, we're getting a lot of traffic, I want to go start up a machine. That's manual. You have to do that. We talked about automation. This does the automation for you. You set the rules for it, and it will do it automatically. So, a couple things you need to know about VM scale sets. So VM scale sets, like everything, have limits. So everything has limits. The only question is, what are they? In this case, 100 machines, currently the limit with a VM scale set. So if you're running an application, like a very large web application, for instance, you may use more than 100. That's fine. You just set up multiple VM scale sets. That totally works. So set up multiple VM scale sets, and again, don't want a single point of failure. So even if you're not doing that, you may say, okay, I only have 50 machines. Great. Set up 2 VM scale sets, and set up 2 VM scale sets, each targeting 25 machines. You'll still have the 50 machines, but now you're protected. If one of those fails for some reason, something happened with your VM scale set, you've got a backup for it. It's all about the redundancy and about building that into the systems. So in this case, you can see I've got 1 VM scale set. Again, put it behind a load balancer. Load balancer is the back-end pool. You can point it at that. In this case, I used 3. You could do 2, you could do 3. But in this case, we're all in one region, and I now have the redundancy both at the VM scale set level as well as at the virtual machine level. So let's take it to the next level. OK, that was great for one region. What about multi-region? The answer is the same. You're going to do the same thing by region, but you're going to set it up in each region, and then you're going to use Traffic Manager, and Traffic Manager is going to point to the load balancer in each of those regions. So now you're being able to spread your traffic across those 2 regions and have redundancy both at the region layer and within the region layer. So more redundancy, slightly more complexity, but allows your application to handle bigger and bigger faults. So next one is network. Let's talk about the network. So load balancing. Everyone's using a load balancer, right? Yes? Sorry, I love these. Easy way to find it. Like, always use a load balancer. So it's important to understand the difference between a layer 4 and a layer 7 load balancer. In Azure, we offer you both. So if you use the Azure load balancer, both internal load balancer or the software load balancer, which faces externally, you're using a layer 4 load balancer. Now, what that means is that it's working at the packet level. So it's taking the packets and it's just routing them fast as can be. It moves them around. It's very scalable, very efficient, and it will take whatever traffic you put in. It's not only for things, many people are familiar with layer 7 load balancers, which in most cases normally deal with things like HTTP, which is great, but sometimes your traffic isn't HTTP. You might be dealing with a different protocol. So this allows you to load balance all of your information on that. But there's things it doesn't do. A lot of times people want a layer 4 load balancer. Or they might want a layer 4 load balancer in addition. So if you want an HTTP load balancer, something like Application Gateway, we'll do things like SSL offloading. Now remember, SSL is only there for HTTP, so it's not there for all your different packets. And so you need to understand that you can do that SSL offloading. Application Gateway is the way to do that, and that's a layer 4 load balancer. Now, you also may choose their third parties. I've listed a number of them here, Nginx, HAProxAir, some of the kind of open source equivalent ones. You've also got proprietary ones from F5 and Barracuda. They're available in the Azure Marketplace. And there's great reasons why you might want to choose these, but if you choose to do them, you're going to need the architecture that I've shown up on the slide here. And this is actually what Application Gateway does under the covers. We do it all for you so you don't see it, but this is what we're doing, and if you're choosing to use your own load balancer, either any of the third-party ones, you need to use this architecture. Because remember, if you have a load balancer and you've spun up a load balancer, it's basically just running, it's just another machine that you're running, it's running code in it. Understand that, once again, you have a single point of failure if you're running one of them. So what you do is you run the software load balancer in Azure, and that's just going to do the packets. And then you create yourself an availability set. And that availability set, you will put multiple copies of whatever load balancer you're choosing to use in that. Your layer 4 load balancers in there. And when you do that, again, you've avoided that single point of failure, because if one of those were to fail for some reason, you always have the other ones that you fail over to. Always avoiding that single point of failure. If you're using something like App Gateway, you don't have to worry about that. We handle that for you. We do the scaling, same thing with the layer 4. We take care of that for you. But if you build your own or you're using other ones, make sure that you use this design, because it will help you avoid that point of failure. So let's talk about the different stages of availability and the different stages of load balancing. So for this, it's probably easier for me to actually do a demo. There we go. So I'm going to go here, and we're going to take a look at what this looks like. You're going to see the glory of my 1997 HTML skills here. But I built this page, and what you're going to see is there's a number of different pages. They're all the same pages running on different servers. What I've done is I just changed the text on those servers so you can actually tell what it is. Because doing a high availability demo is really difficult, because if everything works, it just looks like the site's still up. So to help you understand what's actually happening underneath the covers, I've changed some of the text so you actually understand what it is. So here's me smiling away and telling you that you can tell where the server is. This currently is my first server over in US West. So, OK, and if I hit this server and I refresh this page, you can see that I have 2 servers there. What am I doing? I've got a load balancer, I've got 2 servers that are sitting behind it, and its load balancer is just round robining between those 2 servers. That's what's happening. That's the design that's going on here. So what happens if a server fails? Well, I get to do here what I always would want to do in production but never would, which is I'm going to go in, and so this these happen to be running on Linux, but it'd be just as true if you're running IIS. And I'm going, and Nginx is the web server that I'm using here. So I'm going to kill the web server, which is oddly satisfying, I do have to tell you. So you kill the web server, it's dead. So now what happens? Well, let's flip over to the page, and we'll load the page. And I can keep hitting refresh, and you notice I'm only going to hit server 2. Why? I just killed server 1. Of course I'm only going to hit server 2. So that happens right away. So that's what you do when I'd say, put things in availability set, put them behind a load balancer. This is why. You fail over instantly. And so there you go. So I have the other machine up there, and it's running away, and it will serve, it'll serve these pages until I bring another one up and put it into the load balancer. But remember, we wanted to talk about, different blast radius. What are we protecting ourselves against? I protected myself against one machine taking a hit here. Well, gee, what happens if I then decide to be ultra nefarious and go take the other one down? So now I've killed our second web server. So we saw we were going through a load balancer. We saw I would only hit those two different ones, and now they've all gone down. So what I've kind of created an example of is what would happen if there was a region-level service disruption, if I had something that impacted all of them. Now what's going to happen to my web application? And of course, that's a teaser that I'll get back to. Because I want to talk through some of these pieces. So what do you do if a region fails? That's what essentially I've just kind of shown you, is I created a region failure by just taking down all the resources that are in that region. So this is when you can kind of think through to yourself of, what would you do? Would you use a load balancer to shift to additional resources? Would you use Azure DNS, point at a paired region? Would you use Traffic Manager to change the regions? Would you start up, if you're using Azure Site Recovery, would you start your runbook and start a failover? And then, of course, you could always just go complain to Twitter if you like. One of these is probably going to be your most effective option that you go do. And what you're going to want to do is you're going to use Traffic Manager. Remember all the designs that I put up earlier? We always had those kind of arrows pointing at each other, and it was pointing at 2 separate regions. That's Traffic Manager. That's kind of part of Azure DNS. Separate than Azure DNS, but it works together with it. And you're going to use that in order to be able to initiate your ability to move your traffic to a different region. So it works. You can conceptually think of it like a load balancer at the DNS level, but it works differently. And I want to talk to you about how that works, because it's important that you understand how they're different. And don't just think of them, they're load balancers, they work just like the software load balancers. So I'm a visual person, and I love animating slides because that's how I learn. So hopefully this will help you kind of understand what Traffic Manager actually does. So we've got Traffic Manager on the left here, and we've got your virtual machines on the right. So Traffic Manager basically just hollers out. It's like, hey, you there? And it does that through an HTTP GET. Just sends a GET across, and you can specify that in Traffic Manager, what the address is, what you want it to do. It's usually good practice to have that point at a status page. You can put it at your regular application if you want. The reason why you'd want to do a status page is because the status page one, you don't have to exercise the whole infrastructure if you don't want to. You may be doing transaction stuff that allows you to just see, is it up? But also a status page, you can do something smart with it. You can have it monitoring your entire infrastructure and change the status that it returns based upon the whole infrastructure. If you just hit the front end page, your database could be down. The front end page still returns an HTTP 200 code. Everything looks good. And it thinks that your application is up and running, even though your application isn't up and running. It's not actually functional. If you have a status page and you've set that application to actually check the different layers of your application, and if those all don't work, it doesn't return 200 status code, then it can actually be smart about when it does the failover and how it does it. So that's a best practice that you should do. You don't have to. You can just point it at the front end if you want. That's what I did for this application, because there's no database behind it. But it's going to respond. So the machine's like, yep, all good. Here's your 200 code, ACK. It's all good. So that happens. It gets 10 seconds to do that. So it waits 10 seconds for that response. And then it basically chills for 20 seconds. It hangs out. So basically you got 30-second intervals. And then it says, you know what? What happens if we kill the machine? So that's what we just did. We just took down that region. So it can't access that anymore. Well, Traffic Manager is really good at doing one thing and does the same thing over and over. It's like, if you ever had one of those like drinky birds that sits there and just like drinks the water, goes back and forth, that's what it does. And so it only knows one thing. The whole world's a nail, it's a hammer. I'm going to go request it. So it goes and it sends it over again. But now the machine's not there. That region is unavailable, or at least your resources in it are unavailable, just like what we just did. So it gets no response. Waits for 10 seconds, doesn't get it. OK, no response. I'm going to wait for 20 seconds. Tries it again. Still no response. Tries it again. Tries it again. So it's going to keep trying. It always keeps trying. That's all it does. But after 4 tries, it says to itself, 4 tries, nothing's happened. So remember, it takes 10 seconds to wait for the timeout, 20 seconds in between. So you got 30 seconds, or 30 seconds as a whole times 4. It's 2 minutes. After 2 minutes of getting nothing back, it finally gets a clue. And it's like, OK, this thing's actually down. It wasn't a lost packet. It wasn't something that was just a temporary blip. This thing isn't responding anymore. So I'm going to go and I'm going to update DNS. And it goes and it changes your DNS. Now, it changes it to what you've configured it to. So you configure it. So you configure it to your secondary site. That's your second region, or third region, or fourth region. You can choose what you want. But it goes and it updates DNS. So when someone makes a request now, it's going to get that new request. But there's also a thing called TTL that you need to be aware of. So TTL is time to live. And what that means is that's how long that when someone's made a request to your server, that it should hold on to that. Because our servers all think in numbers, IP addresses. We usually think in names. So when I'm doing something like the Traffic Manager demo, trafficmanagerdemo.com, it's going to know that, and it says, I don't want that latency, and I don't want that load on my DNS for it to look it up every single time someone's doing a request. So the TTL is how long it holds on to that. How long should your clients hold on to that before they re-request it from DNS? The default with Traffic Manager is 300 seconds, does it in seconds. That's 5 minutes. So it can be up to an additional 5 minutes before the client that's requesting this actually gets access to it. But the TTL is configurable. Like I said, 300 is the default, but you can lower that as low as 30 seconds. So you can drop that to 30 if you want. The benefit is these things will update faster. The downside of that is you're going to have more hits that go to your DNS. There's going to be more latency as more requests go through on that. So you have to strike that balance on what you want to do. If you're looking for kind of a quick, easy way of like, hey, is there any way I can short circuit this? There is. So I've set this up. You can set up Traffic Manager to work different ways. You can choose performance-based routing, or you can choose round robin, or you can choose weighted, if you want to weight things between 2. So you can cheat a little bit if you want to, if you're actively managing it, by changing it to weighted, and then just weighting the other region much higher. Weight the other region 100, rate the region that's down to 0, and then it'll switch over faster. But if you're not doing that, if you're letting the system just run, it happens at a time when you're not monitoring it, it'll happen, and it'll wait for the TTL to end. Now, for the person that just got it a minute before, it's going to take the full TTL time. For someone who's just requesting, it'll happen instantly. So realize that there is a gap there, and the gap is going to vary depending on what the client that's accessing it. So it goes, it updates DNS, and of course, now your clients can go through. What happens when it comes back online? So OK, you fixed the problem, the region's back, your machine's back online. Now what happens? Well, like I said, Traffic Manager is just that little bird keeps drinking. And so it goes, and it's always requesting. Even when it's down, it keeps requesting. So it does the request again, and this time it gets a 200 code. It's back. And as soon as it sees that it's back, it doesn't try it multiple times. As soon as it comes back and it sees it once, it goes and it updates DNS. Now, you still have the TTL you need to think about. But remember that it's 4 tries through times 30 seconds for it to make the switch over. But it's only the first. As soon as it sees it back, it automatically updates it. So that's what happens with Traffic Manager. And that's why it's a little different than your standard DNS. So I talked about the different ways. Performance is basically it's using latency. It's seeing when someone connects, which region, which of the endpoints that you've pointed out has the lowest latency that it sends it to. Priority is just you can pick priority. In this case, I picked the priority to go to US West, because that's where I had the multiple resources at. And then weighted is, like I said, you can choose. That's really useful if you want to do things like A/B testing. You want to have 2 different versions. You want to send 50% of your traffic or 20% of your traffic to something and see what happens. You can do that through DNS. So let me flip back to our demo station here, and I'll reload this page. And you'll notice now that it's saying, hello, server 1, East US. So before we were in West 1 and 2, now we're in East. Traffic Manager has failed. Everything that I basically just explained, that's what's happened on the back end, and this is running. I didn't go and change anything, but the time we were talking was actually the time that it was failing over in the back end and updating DNS, and the TTL was expiring, just like we talked about. So that's what it looks like. Like I said, high availability, not sexy, super important. Now let's talk about storage. So Azure has 4 types of storage accounts that you can set up, 4 different types of storage and how they handle them. I'll go through them quickly because I find that not everyone understands what the differences are, and then I'll talk about what you should be using and when you should be using it. So LRS, locally redundant storage. Basically think of it as within the storage rack, you've got the equivalent of 3 different copies stored locally within that rack. Rack goes down, your storage is offline. So no particular one will be down, and we spend a lot of time making sure that we optimize for 0 data loss. So you've got multiple copies there, or the equivalent thereof, based on the technology that we're using. But your scope of what could fail is basically at the rack level. You've got zone redundant, which basically you've got 3 copies spread across 2 to 3 different facilities. So you've got the same number of copies, but they're spread out a little more broadly. And so you've got a little bit more protection on what you're doing there. And obviously, each of these is basically a trade-off on cost versus your data availability. The next level up from there is GRS, or geo-redundant storage. In this case, we keep 3 synchronous copies, just like LRS, basically. And then you've got 3 additional copies that are stored in a different region. So you've got 3 more copies that are somewhere else. And that's stored in a paired region. We'll talk about paired regions in a minute. But basically, they're somewhere else. So if an entire region is down, you know that even if that region burned to the ground for some reason, you've got 3 copies that are stored somewhere else. And then finally, you've got RAGRS, which is the same thing as GRS storage, except for that secondary copy that you have is actually read accessible. And the easy way to test this is just go to any account that you have with this. If not, just go create one and take the URL for your storage account and just add -secondary onto the end of it. So if your account name was blob, you could do blob-secondary, and you would see you'd be accessing the secondary copy of your storage there. So those are the differences between those, and they're true for tables, blobs, queues, files, everything that you do in storage. When you have a storage account, you can set it up and you can choose this setting for each of them. Now, the key takeaway when you're thinking about storage is you can ignore those. Don't do them. Now that I've told you about it, I'm going to tell you what you should do. Use locally redundant storage, especially for your disks and your VHDs. You're not going to put your VHDs in something like, read access GRS, because you're not going to be syncing that data constantly, and you're not going to spin them up anyways. Your machines are local. You might do something like your data disks, have your data over, but the machine and the disks that you're running, that's actually your C drive, say for instance in Windows, do that in LRS. Now, your data and the things that you want to be able to be accessible, if you ever had to do a failover, if you're ever doing a disaster recovery scenario, and you want to be able to access it, you want to access it on your terms. And accessing it on your terms means you need read access GRS. Because GRS, the data is stored and it's there, but you can't access it. You don't get to choose when you get access to it. It's there for us to be able to restore it and make sure that we've held on to your data. We make you the promise that we do everything we can to make sure that your data is secure and protected, even if something like a data center were to burn to the ground. But we're the ones who will go and restore it. If you want to own that decision, if you want to decide when you're going to do that failover, when you're going to copy it, you want read access to it. And that's what RAGRS is good for. So think of using those 2 storage types as what you're going to use for either your data or your disks. So I talked about paired regions a little bit. I also, one more thing on the storage is use the Azure SDK. If you use the Azure SDK, it has this wonderful feature in it where it will check, and if storage is unavailable, it will automatically check the secondary region if you're using RAGRS, which means you don't have to write a lot of complex code. You just go, you use that API, and when you go to access it, if it's not able to access it, it'll automatically retry the secondary region for you. Just makes it nice and easy. Paired regions. Every region in Azure has a paired region. Paired regions are there to provide you a number of different benefits. So I have a list here. Sorry for the small text. This list grows and grows. We grew it this past month several times, and so it's unfortunately it gets larger, but if you ever want to look at the active list, there's the URL at the bottom of the slide. But this is important because it provides you isolation. When I say isolation, like each of these regions are geographically separated. So you have the regions, and they're at least 400 miles apart. There is an exception to that. That's Japan. It's because it's very difficult to actually have 2 data centers that are 400 miles apart. But all the others of them, they're at least 400 miles apart, which means you're in different climate zones. It means, if you had a flood, if you had a hurricane, if you had a blizzard, you're protected from that. You don't have a data center, you're like, oh, my DR site is across the street. Okay, are you actually on different power there? If it flooded, are you just going to flood both your data centers? So they're made sure they're in different flood plains, and sometimes they're even in different tectonic states, or on different tectonic plates. So it's about providing that isolation. And also providing the replication. I talked about the RAGRS, and that we have services that automatically go and replicate some of your data, make your services easy to duplicate across those. It's also important to understand that if there's ever a large incident that happened in Azure, there's a region order to things. And the first thing that we try and do is make sure that we bring up at least one of the region pairs in every geography. So if you don't choose to be as part of a region pair in your geography, you could pick 2 different regions, and they both could be the ones that came up second, which you probably don't want. You probably want to come up as fast as possible. Making sure you're using region pairs ensures that at least one set of what you've built will be part of the first things that we bring back up. The same is true with updates. Just like you had fault domains and update domains, there's the things that are terrible to happen. There's also about when we're rolling out updates. And we make sure that we're not doing them in both regions at the same time. So if for any reason there was a problem with one of the updates that was rolled out, you could be sure that one version of what you were running wasn't impacted by that update that was rolled out. Versus if you picked 2 regions on your own, they could be 2 regions, and we don't make that promise across regions. So you could pick one where we roll them out both at the same time there. And then you could be impacted by something that happens. And the final one is just data residency. We know that many of you have compliance needs around things and making sure that if you want to be able to have your data all stored in Germany or all stored in China or in the federal government cloud in Canada, UK, all of these places, that we've got dedicated regions where we guarantee to you that your data will stay within that region. And if you want to be able to do multi-region deployments, you can and still stay within that geography and still meet those data residency requirements. So I talked earlier about there's also, you got to be aware that you could have a single point of failure with storage. Everything can be a single point of failure, and the goal is always remove single points of failure. So one easy one, always use premium disks for production. Dev test, you can do whatever you want. For data disks, go ahead and use whatever makes sense for you. But for your production machines, especially for your OS drives, make sure you use premium storage. That's SSD storage, basically. And that's all about IOPS. It's making sure that you have the right IOPS. Another thing is you can put more than one machine in a storage account, but you have to be smart about it. So one, never put more than 40 machines in a storage account. And if you're doing custom images, if you built your own versus you're using the ones that we have, don't do more than 20. The reason for the difference between the two of those is we have a caching layer. And so the images that we've built sit in a caching layer, and so not all that traffic actually goes and hits your storage account. But if you're building your own VHDs, then those are going to be custom. And so you've got a different number of how many you can have. And there's IOPS limits, and you need to watch your IOPS limit. I was dealing with one customer, and they were having problems accessing. They had a lot of availability problems. There were failures, there were kernel panics and blue screens. And we took a look. And it turned out they had 350 machines all running out of the same storage account. Well, OK, what happens? Well, you've got this IOPS limit in there. So let's say you're looking, make all those requests, and they're not all going to get fulfilled when all those machines are running. So if you're trying to access something like a static asset, a picture or something, that's probably fine. Probably doesn't matter all that much. You'll get some latency on it. Maybe it won't come back. But if you're writing to, say, your swap file, that's going to be a problem. You'll blue screen on that. And that's what was happening. So make sure that you understand what's happening. In general, think about spacing out your storage accounts. You can use them for servers that are in different tiers of your application, but don't take the same server in the same tier in the same storage account. Again, because if you do that, and for some reason something happened to that storage account, or whatever storage stamp that storage account was on, then the problem is you hit multiple. The idea of spreading them out in the availability set that we talked about earlier has just been negated by the fact that you've got a single point of failure on the storage piece that when it goes down, all those machines go down. So spread those out. If you have a premium support contract, you can contact support, and they'll help make sure that you can spread those things out across they'll take a look and make sure you're in different storage stamps, that you don't have single points of failure for that, and they'll help you with that. But I also want to show you a tool so you can kind of figure these things out yourself. And you can look at that, and you can know if you have these challenges or not. So I'll do a quick demo here. And the next slide I bring up has the URL on this, so don't worry, you'll get the URL and all that. So once again, my awesome HTML skills at work here. But this is a tool. It's publicly accessible. You'll be able to hit it. And you can just put in a storage account. So in this case, we'll do test. This is actually for those of you that geek out over interesting architectures. This is actually a serverless architecture. This is a web page that's served out of a storage account. And then the processing actually happens as an Azure function. There's no web server. It's actually involved in this. It's just kind of a fun thing to build. But when you run this, what you're going to see are two things. You obviously know what region you're in. But you're going to see a data center ID, and you're going to see a stamp number. And what you care is that those two numbers are not the same for something. If those are both the same, within a region, then what you have is you have those two machines have a single point of failure. And if those are, say, in the same tier, then even though you thought you might be spread across an availability set or had two separate machines, you now have one spot where that could fail. And this tool works, obviously public cloud, but you can also use it government, China, Germany, any of the sovereign clouds. It also works with it. So you can poke around with that tool if you like, just to kind of know. Of course, it's neat to poke at it, but if you're going to do anything where you really want to do this and go through, say, your whole infrastructure, you're probably going to access it programmatically. So the URL at the top is if you want to do the web UI, but you'll see right underneath it, I have access to actually the Azure function that you can access directly. It's a publicly accessible endpoint that you can go hit. And basically, if you post, and I show you what the JSON call is, you make a JSON call in that's basically the URL for your storage account, and it will return a JSON blob that has all those different pieces in it. So if you wanted to go, I saw one person actually showed me the other day, they'd built a comparison tool where they take two storage accounts in, and they tell you if you've got a single point of failure between them or not. So you can make calls to this, but this allows you to look at things. And so if you wanted to say, hey, I've got a single point of failure here, or maybe I want to spin up another storage account, make sure it's on a different storage stamp, and then put my VHDs there when I'm spinning something up to make sure I don't avoid it. This is a way that you can do it. I do have to call out that this isn't a tool that's officially supported by Microsoft, just something that I built. But it's up there and running, and you can play with it if you like. I just wanted to kind of make that available because I think it's far better for you to know what's going on with your resources and what you can do than not know. So let's talk about common architectures. So databases. I mentioned databases before. We got to go through the different consistency models, how you think about them and how you design for them. So my guess is everyone here is probably familiar with RDBMS SQL databases, right? This is like old hat. Everybody knows this? Quick check for a weakness? Yes. Good. So this provides you strong consistency. This is great for things like financial transactions. It's a great example. The quintessential example of this is you do not want to be replicating your SQL database between, let's say, like, Shanghai, London, and Seattle. And you're going to synchronize them, and then someone figures out, hey, I can do this transaction where I can make a request to, say, withdraw $5,000 or transfer it to an account. And if I submit it to all of them at once, they don't talk to each other. They're on this slow update between them. They're asynchronously updating. And so they'll all say, that's a good transaction. Go make it happen. SQL databases help you protect against that because you can set it up to make sure that your data is strongly consistent. You can make sure that when a transaction goes through, the other ones are queued up behind it. Now, the downside to that is there's latency with that. If you're going to copy your data all around the world and you're going to make sure and then verify that that data copy happened and you're going to queue up all the transactions that happen behind all those, that's going to slow down your processing. And so although you may say, hey, you know what? For large money transfers, that seems like a perfectly good trade-off. That may not seem like a perfectly good trade-off for something like, say, an ad server, where you might want something to move super fast. So it's important to understand the benefit you get from strongly consistent, so all your data will always be the same across all of them, but there's a latency hit depending on how far apart they are. So with SQL Server, you think about things like using always on. The thing to remember with that is latency envelope. So 6 milliseconds latency envelope for synchronous, always on for SQL Server. Beyond that, so if you're doing, say, between regions or around the world, you're going to be an asynchronous replication. And asynchronous means they're not all the same at the same time. So next step on that is taking a look at something like, NoSQL databases. So these are eventually consistent. They're the other end of the spectrum. What it says is you're going to be super fast. Things are going to happen really quick. That's great. There's no guarantee that what you're getting is actually the latest data and that it's all consistent amongst them. So this might be good for like games, leaderboards, things where people want to see updates right away, but it doesn't really matter if there's a consistency challenge between the two, that'll net itself out in a few seconds, and that's totally okay for what you're doing. And then, of course, there's a middle ground between the two. So DocumentDB is a good example of this, and this is about session consistency. So this would be something like, think about if you put a post up on Facebook or LinkedIn. You want to see that you put that post up right away. If you put a post up and then you hit done, submit, and nothing shows up, that's going to look weird to you. And so it makes sure that within your session, it's there, it's consistent. But what it doesn't guarantee is that that's synced to everywhere else. That will happen later. And so your friends' feeds might not be updated for a minute or so. And if you posted a new picture or if you've gone and done an update, that's probably okay. But these are 3 different models, and you handle them a little bit differently. So it's important to understand which are the ones you're going to want to choose and how you do the replication. Because replication for things that are eventually consistent or session consistent are much easier because you can replicate those around the world. You don't care. It's not a financial transaction. It's not going to impact you that much. versus things that are RDBMS, like SQL, you do have to make sure that you're making those decisions around the impact there. So let's take a look at our architecture, what that looks like. This is your standard 3-tier architecture. And you've got the 3 tiers like we talked about. You notice we also put a distributed cache here. And this is really about performance and scalability. Distributed cache in Azure, use something like Redis cache. And that basically is an in-memory database. And so you're not hitting your SQL servers. You're freeing up those resources in order to be more scalable. And so this looks like what you've probably been doing for years. So I won't spend a ton of time on it. Want to talk about multi-region deployments. So before I talked about active-passive. So remember the passive ones, and I'll show you an example in a second. We'll bring it back up. But basically, you've got one version that's sitting in one region, and that's the one that you're using actively. That's the one that's at scale, that you're running, that all your users are being trafficked to. But then you've got traffic manager that's aware that there's a second one out there, and you're not using it, but it's just got a few resources that are up and running that sit there just in case you need to fail over to it. So it's really one region with some failover, and you're doing that by running things that are reserved, that you're reserving your capacity. Now, active-active gives you a much stronger environment. You've got the ability, when you fail over, remember, you're going to need to scale up that second environment. Active-active is already scaled up. You're already running actively in both environments. So a little bit more expensive to run that, but the biggest challenge there is thinking about your data layer. Because again, if you're running active-active, you need to think about the concurrency model for your database, and what we talked about on the last slide. And the more you're using things like SQL databases, the more you need to think about what's the latency impact to your users. You don't need to worry about that when you're doing active-passive. You do need to worry about that if you're going to try an active-active design. And then active performance is kind of a hybrid of the two. It's basically using Traffic Manager, where you're taking a look at the latency between the two, and you're basically running active-active and then routing users to either location rather than just one location based upon where they're located to make sure that they get a better performance. So OLTP is online transaction processing. So here's an example of one of the setups that's been set up. And you'll notice, the giveaway I talked about before, asynchronous between the two regions, between SQL. So that means you're talking about active-passive. So you've got one version that's always up to date, that's running. The other one's there, available to start up if you need to if you fail over quickly. If you're doing active-active, you notice that everything else basically looks the same, but we've changed what the database is. We've now moved to one of those session-consistent databases, something like DocumentDB, to make sure that we have the session consistency, and we can sync that over, and we can run active-active. Different database model, be able to have that active-active design. So quick example of one place where we've done this. I worked with a solution architect who worked on the 2016 Democratic National Convention. That website was actually set up on Azure. Set it up to be highly available, set it up to be cross-region, really high scale, as you can imagine. Politics this time of year, there's a huge amount of load on that, and 6 months from now, the website will probably be gone. So really great for cloud in terms of the ability to scale. You can see at the bottom, I've got a chart here, shows you what this is actually the real traffic chart that we saw on the website. And we were hit with a DDoS attack on it on Tuesday. And we handled that DDoS attack because we designed something that was highly scalable, that was spread across region, that could handle someone sending a tremendous amount of traffic and data at it and be able to handle that without worry. So what that architecture looks like, I apologize for the eye chart here, but this is what real architectures look like when you build them out. I'm going to ignore the security stuff simply because we don't have time to go through that. But we were using Azure CDN at the top of this. We're using CDN for DDoS protection and be able to scale those pieces out. This happened to be built on Linux. We were using an Ubuntu server, web server. And we had a number of those. Again, availability set, sitting behind a load balancer. Hopefully you're noticing the pattern in these. And then MariaDB. So MariaDB, for those that aren't familiar, is a NoSQL database built for scalability. So we use that as the database that sat behind this. And then there's, like I said, there's some jump boxes and AD and Key Vault, and that's really security stuff. If you're curious, I would love to talk to you about it afterwards, but it's not tied to the high availability stuff that we want to chat about today. And we duplicate it across regions. And so you could have this available multi-region, so even if something impacted one region, we were available in another. When we were done with the event, when the event was over, one of the regions was shut down. There was no reason to run multi-region in this particular instance. It was about making sure we had the availability for a very high-scale event that happened. So I want to talk a little bit about CDNs here. I mentioned them earlier about making sure that you put stuff as close to people as possible. CDNs, they're great protection from DDoS, but I want to talk to you about the availability piece. Like I said, there's security stuff in there as well about obfuscating your origin, but really, this is about offloading a lot of the resources that get soaked up from your machines. So when people are hitting your machine, like They're hitting the machine has to process that stuff. When you move things to a CDN, it takes a lot of that processing and it moves it off of your machine. That means that your machines are more scalable without having to actually buy bigger machines. It also means that it's available everywhere because CDN, so Azure CDN gives you two options. You can use Verizon or you can use Akamai. And they have literally thousands of spots all around the world. And when people make a connection, they're going to make a connection to the CDN first, get all the data they can from the CDN, and then they'll hit your origin. Then they'll hit your server. So it takes a ton of load off of your server. So I want to give you a quick demonstration of what that looks like and why it matters. So I'm going to go and open an incognito window here. The reason I'm doing an incognito is because I've hit this page before, and otherwise I'd just be pulling it out of the cache, and it wouldn't show you anything, although it would be remarkably fast. So what you're looking at here is a web page that has 3 iframes in it. The 3 iframes are all served off the same server. Everything here is served off of a server that I've got in West US. So got a server, it's serving these pages up, and basically, if I click on each of these, it's just going to load a page from it. So it's got a timer, and it basically just times how long it takes and tells you that. It's a set of various monkeys. If anyone recognizes Naru in the picture, that's awesome. He's the monkey that took the selfie. He's the one in the top right. Some guy left a camera in the forest, left it, and the monkey actually took a picture of itself. So that and a bunch of friends that I have. And so that took a little over 10 seconds to load. And that's just a timer that's running. Like I said, the server there, I put the pictures on it. This is all live. You can hit it on your own machine if you want. The only thing to be aware of is I chose 6 pictures because that's the limit of how many concurrent connections that your web browser will allow. So I didn't want to be impacted by a browser saying, OK, I'm going to delay certain numbers of them. And the pictures, although they show up small in this example, they're actually 8 megapixel pictures, and I haven't done anything like gzipping them. The reason I did that and I put it on a small instance type is because I wanted to show you the impact of putting load on a server from one machine rather than having to spin up a whole bunch of machines and have them all hit it to show you what load meant. So I've just scaled it down. You could scale it up. You'll have the same thing. You'll just have to hit it with more people. So when I hit this one, pulling it out of a storage blob, this is the same thing. It's the same web page coming off the same server. The only difference is I've taken all the pictures, and rather than serving those pictures off of the machine where I'm having to run the machine to process them, I've moved them out to blob storage. So a great scalability choice is to take your static assets, anything that you have that's static, put them in blob storage, and then just point to the blob storage where you pull them out. So you can see it's less than half the time. It's the same page. I just moved the assets out to storage. It'll not only be cheaper and help you scale better, but also, you notice the time difference? There is one trick here that I want to point out, which is the web server here is in West US. But the pictures that you see loading for that second one are actually in West India. So even coming halfway around the world, it's still half the time for your user experience on these. But of course, we can do it one better. And I'll show you the CDN. And that's real live load there. So that's the same thing, thank you, of what I did basically is I just took Azure CDN and I pointed it at that same server. And so what's happening is rather than having to go to West US and pull it, it's actually contacting Azure CDN and pulling those static assets down. And so you can have a load time that is literally orders of magnitude difference for your customers. Like I said, this is real code. If you want to take this URL, hit it on your own machine, you'll see the same thing. Just don't do it on the conference Wi-Fi, because then what you're really going to be testing is how overloaded the conference Wi-Fi is. You'll see huge numbers, and it has to do with basically the Wi-Fi. It has nothing to do with the network. But if you get on a hard line, try it, and you'll see it. So that's the kind of availability challenges that you can see using a CDN. So not only do you get the security benefits of it, but you also can create a lot more availability and take a lot of load off of your servers. So I already did the demo. The last thing that I want to talk about today is fault injection. So remember when I said trust and verify at the beginning? So how do you verify it? And the answer is you test. Always test. It's like one of those habits that gets drilled into you. And I'll admit that my early days in engineering actually started as a tester. And so this is close to my heart. There's a great tool out there called Chaos Monkey. It's created by Netflix. They designed it to work with AWS, but you can convert it over. You can use with Azure. There's a lot of other fault injection tools out there as well. I don't have any particular tool that I'd recommend over another. You'll pick whichever one's right for you. What's really more important is that you're doing the testing, not which one you're choosing to do it with. If you actually want to kind of try out what it's like to be your own Chaos Monkey, we actually We built something that's down on the show floor if you come by our booth, where you can play a game that we built. In the game, you go and you shut off servers, you whack servers that are flying around the screen. And the neat little trick to it is all the servers that you shut down in the game, you're actually shutting down the actual servers that are running the game. So you can go and try and create downtime by trying to take it down within the game. We did that to showcase some of the availability stuff, and I'd love to show it to you all. But you get to play the Chaos Monkey there. It really doesn't matter what you're doing. Just go in and test. These are the things that help you find that. Remember I said, if you take nothing else away, take away that single points of failure are bad. You need to get rid of single points of failure, and this is a great way to find those single points of failure. Go in and do fault injection. Go in and just shut things down, see what happens. If you're afraid to do that in production, realize what you're telling yourself about, how brittle you feel your infrastructure is. That's okay, you might not be there. Set up a test environment and go and do it, but understand what that means. When you're setting up that test environment, you should be using the automation and scripts we talked about earlier, because then you can be sure that you have the exact same thing that you had previously. So use that automation to set it up. Go ahead and hack at it. Find where these things are, because that's the way that you're going to make sure that you set these things up and you get better at it, that you make sure that you know that you're indeed fault resilient. Because you can say that you are, but until you've actually proved it, that's when you actually know that you are. So let's wrap it up. So we talked about designing for high availability. Talked about understanding best practices and common pitfalls that are in it. And I talked to you a little bit about some of the inner workings of how we built some of the Azure stuff itself. If you want more information, here's a bunch of articles that we put up, and there's more available. It's all available in the slide deck, by the way. The slide deck will be available, so you can download the slide deck, and these pieces are up on azure.com. If you download the slide deck as a little added bonus, at the end of the slides, I actually added a slide on high availability checklist, so 15 things to go and look at in your infrastructure and see if you have them. Make sure that whether you have them or whether you don't, so you know, are you missing best practices? So it's a quick, easy test that you can go and do. It's also related content, other sessions. I mentioned earlier before, some of you are interested in disaster recovery or other parts. Some of these have already happened, so you can look up the recordings online or in the app. Some of them are yet to come, the ones closer to the bottom. So if you're interested in some of the disaster recovery pieces, remember I said this was about high availability. Resiliency goes to the other end with backup and disaster recovery. There's some sessions you can go to learn some great things about those pieces. And please, when you have time, fill out your evaluation. It's how I know what you want to hear from us, what we can do to be better. Microsoft takes the time to fly me out here so that I can talk to all of you, and it really is important. We do it to make sure it's better for you. It's not so I can be on a stage, it's so that we can help you learn what you can do to be successful in your applications and what you do in your enterprise. Please take the time to fill out. It helps me get better. It helps me provide better information to the people who come to Ignite next year. We appreciate that. There's also some additional resources that are available just general for IT pros. And for those of you who have to run to your next session, I will say thank you very much for coming. It was an honor to present to you, and I appreciate your time. Thank you. And with that, I've got a few minutes for Q&A. So if you want to come to any of the microphones, I'd be glad to answer those. Otherwise, if you can't make it, I'll be down at the booth and happy to answer questions there as well.
Hey there.
Hi.
In all of your great diagrams, there was still some points where there was a single image, and that was, of course, the Azure load balancer, which is highly available. Mm-hmm. Do you have any insight how they architected that to be highly available? Do they use round robin or some of these other techniques, or is that secret sauce that we can't talk about?
So I can't talk about what the actual underlying architecture of that is. What I can tell you is that we've designed it to be highly available so that there's no single point of failure within the load balancer service to make sure that you're not hit with that.
So if we're using two load balancers on two separate layers of our application, we don't have to worry about those both going down at the same time or anything like that, well, region-wide?
I can never say that you can. There's always something. If storage went down, if the region was hit by a meteor, I can never say never, but I can say that it's designed for high availability within that region. And then if you need to be across region, then you would look at something like Traffic Manager to load balance it to a different region. But yes, you can. Thank you very much. Oh, sorry. Yes?
So for availability sets,
yes.
are they specific to premium storage only, or is there availability sets for other types of storage besides premium?
So availability sets are available regardless of the type of storage that you use. That premium storage is recommended for your production workloads for running your system drives on. You'll just get better performance, better I/O, more consistent I/O. But availability sets are available regardless of what kind of storage you're using. So even if you're doing your dev test workloads and you're using those on standard storage, you should still use an availability set. Yep.
And should you use, so say for your example, VMs, right? If you have availability set, can you put the same VMs in the same storage account, or is it best to have availability sets between two storage accounts?
So within an availability set, you should always make sure that your VMs are in different storage accounts, because those are the same tier of application, and if you put them in the same storage account, you're guaranteeing that you will have a single point of failure. So within an availability set, which by definition is a tier in your application, you absolutely want them in different storage accounts.
Okay. Thank you.
Thank you very much.